project? Remember we just rotate it, right? Is it?
Yeah.
Let's rotate it the other way. Okay, so view, set 3D view, X, Z. So that's looking directly on. I thought this looks funny. Is this how we left it? There are no restraints. Didn't we restrain this from having modes out of line? Or is that this one? Maybe that was before we added more elements. Is that what happened?
Just
Yeah.
All right, well, let's restrain all of them. Ready? Oh, we can't. We gotta unlock it. Before we unlock it, let's unlock it. So this really forces it to act just in the point. Okay, so Y, then out, Z, that rotation around. That should be restrained, not this rotation around. Is that correct? I'm gonna mess it all up. Say okay. So let's rerun this one. So where were we last time? Running the linear elastic time history analysis, right? And how much displacement did we get at the top of the bridge? Maximum?
6 feet.
No, I think from the earthquake it was about 0.4 feet, a little less than 6 inches, right? It was the ARS curve that we got, 0.6, which is about 7 inches. And that's because, let's see. Yeah, we're going to try creating a video too. Let's do this first. So joint 6. 0.4, just over 0.4 feet, so that's about 5 inches of displacement. That's it, you can see it right here. If you want, you can zoom in, display it again. Let's say between 4 and 12 seconds, okay? And you can always save this as a file into Excel or some other program. See, so you can see what the vibration characteristics look like. Then you just go back here to reset default. Let's say we want to know what the moment is at the bottom of the column here. So what did we say we're going to design the column for? What moment capacity will it actually have?
1/6 of the.
About 5,000 kP, right? Something like that. Well, let's see what the, let's click on here. And let's, as an example, pick this member, right click on it, it's member 26, okay? And then we'll look at this one too. This one, I'm right clicking on, it's member 30. So 26 and 30. So what we do is to say display, show plot functions, find plot functions, add plot functions. Oh, what happened? I want to go over to frames. So, add plot function. I want moment 3.3 for element 26. So that's, and it's at the 0 location relatively, not at the top but at the bottom. I think it's at the bottom. We can go check. And then add another one, and at 30. And moment 3.3. Say okay. Okay. We'll come back and look at these in a seconds, it's done. I want to go back and look, this is the 26. It's looking at location. It starts at joint, that's the I is the starting and J is the ending of any member. So it goes from 3 to 23. If we click on here, that's 3. Okay, so 3 is the beginning. And then let's check the other one. It starts at joint 5. So let's make sure it's joint 5. Okay. So what we're doing is we're pulling the moments out at the 0 location at the beginning of the member. If we wanted it at the other end, you'd say 1. It would be at the top or any value. Okay, so let's now go back and look at that. In units, we're in kips and feet here. So display, show plot function, move that over, and then we can double click this like that. Or you can just click on one like this, frame 26, click on add. It's going to give you frame 26, the moment, at the bottom there versus time. This is the horizontal axis there, see it's display. And so it looks similar to the displacement plot because it's proportional, so linear elastic analysis. So the moment varies over time in a similar profile. But now look at the values. Here we have what? Over 20,000 kip feet. See, it's 20 times 10 to the 3. So it's 20,000 kip feet. The maximum is 20,065. And we said that we have a column that we're going to design with about 5,000 kip feet. So we want to recognize that nonlinear. We can do that. Let's look at the other one. So frame 30. And it tells you up here what it is. See, frame 30, station 1, that was at the 0 location. Moment 3 here. And this one also is exceeding 5, but not by as much. The maximum is about 12,000 something. You see over here it says maximum is 12,300. In the other direction it's about 10,000. But it definitely exceeds the moment capacity of this column. And the reason it's different, of course, is this column is longer, more flexible, so under the same lateral displacement distance, picking up more moment. If you look at the top, the moment will be less at the top than at the bottom because it's the superstructure and flexibility that's relieving some of that moment. Okay. We can take a look at that too. In this case, let's right-click on this one. My mouse. Okay. I don't know what this is. Version 15. It's fitting now. Okay. So let's try it again. Right click on that. Okay, that's 29. Oh. And the joint here is 25. So let's go back and right click on here and go to this. It starts at 25. So we want it at the top, right, where the moment's the largest. And again, this is 29. So say display, show plot functions, find plot functions, go to down to add frame forces, add plot function, and then we type in the ID for the member, which is 29. And in this case, we put, you can do relative or absolute. I don't know what the actual length of that little segment is. I'd rather use relative then. And instead of 0, I'm going to put 1. That way it'll be the moment at the top of that little number. Let's say OK. Oh, that'd be axial force though, right? I want moment 3 to create. That's what I'm interested in. So they say OK. So it's 29. Move this back. And you can see it's definitely smaller than the moment at the bottom. The moment at the bottom is a maximum just over 20,000. Here we're seeing, it's interesting, this direction is 16, and this one we're seeing 18,000. So it's smaller, but not a lot smaller. What we want to do is let's create an ARS curve. Let's create, we developed, we put in like a design type envelope response spectrum curve, right, last time. I want to find out what is the actual acceleration response spectrum curve, the ARS curve, for this particular earthquake. And then SAP can generate it for you. The earthquake's already in here, right? We gave it the function file. So what we can do, and we already ran it, But we can say, okay, let's go back down to this joint. You have to pick a joint that's at a fixed location, because that's where the earthquake's coming in. Right click on it, and it's joint number 3. You can use any of these, and you get the same results for it. And then click say display, show response spectrum curve. See? It's right there. Tells you. And you say joint 3. Over here on options, I don't want it to be a logarithmic curve. I want it to be arithmetic versus arithmetic. So rather than log or log arithmetic, it's much cleaner. And then define, okay, it's telling you which, this is the earthquake time history, it's the only one in there, but if we ran different earthquake motions, you could pick different earthquakes or different loading. So this is fine. Axes, the horizontal axis, do you want frequency versus or period? I want the natural period of the structure versus this is a spectral acceleration here in the vertical. Let's see what else. Direction, I want it in the x direction. That's the longitudinal direction in our model. Damping, it's going to give you a bunch of plots. I don't want all these. I only want it at 5% damping. So I'm going to say delete this one, delete that one, delete that one. Don't delete that one, so I'm going to skip on to the next one. Delete, delete. Okay, so there's only one curve it will plot for me. Let's see, direction, period, axes. I wanted to say plot. I didn't see it, so I said done. I was hoping that would be plot, but it's not. Let's try it again. Okay. Oh, you know why? I don't think I clicked on add joint. Okay. So I'll go back and do the same things. There's display down there. So that's what our actual ARS curve looks like for this earthquake. If you remember, I created a fake, well, this is actually feet per second squared here, it's not in G, right? So let's keep that in mind. And if you remember before, I had it look, not exactly like, but it went up, it went over, went down, and then over, right? And so the idea is that if this is one spectral plot, if you generate other ones, you'd have other curves that look different from each other, but overall similar trend, and then the envelope goes over all of those. And for design purposes, it's like we've looked at all the possible earthquake motions. But what I want to do is save this. So let's say File. Let's say Print Table File. Okay, and then we'll call this ARS for our bridge. Save it. So we created an ARS curve. So let's say we had, it doesn't have to be created in this program. You can get ARS curves generated. They come from different places. And then what I want to do is run this, rather than a time history analysis, run this with that ARS curve and compare it to the maximum spaces and moments we just got. Okay? So I'm going to unclick that, say define, load cases. Go back to we had a response spectrum analysis we did before, so go back to that, and we'll use a different response spectrum curve. Let's say, so to do that, we have to actually go back to functions. Define functions, response spectrum. What was it, which one did we create? Function 1? Yeah, remember we created this? So now what we're going to do is we'll bring another one in and call it something else. So we can look at this. This is in G. The other one's in feet per second squared, so we'll have to change the modifier. So what we'll do is say from File, add new function. And then we have to browse sus function 2. And then wherever you save it, you go get it, right? sorry, you see all the header stuff? If we don't type in the right number, it won't work. Watch, let's try it. It's got to be period versus value, but if we hit display graph, see it's an error. It's error in reading. So now we'll go back to view file and see how many lines, header lines it just get. This one too, right? So 16 total, because this one just says the damping level. It's just information. But this actually provides the natural period structure versus the period. I'm sorry, versus the acceleration. This is where single degree freedom possible. So let's see if 16 works. This is header lines to skip, put in 16. There you go. So it brought it in, right? SAP's now recognizing this. Like I said, we created it using SAP. The SAP doesn't know that now. It's just a text file. You could have created it in any other way. So then I could give you an ARS curve and say, here, do this. This ARS curve is particular to this earthquake motion that we're using from the 1989 Moment Curvature earthquake. And the way this is generated is, if you imagine this is the natural period this way, let's say a single degree of freedom oscillator, this is the acceleration on the vertical. And so if you have something that's solid concrete slab bolted to the ground, it has essentially zero natural period, right? It's solid, it's rigid, it's just this thick, and so it's going to accelerate to the ground. And so the period is zero, so you move to the left, and then this would be the acceleration of that slab, and it's the same as the peak ground acceleration. And it's the maximum acceleration of the whole earthquake motion at that slab, which in that case is the same as it follows the accelerations to the ground. Now let's say you have a more flexible structure, let's say about here. This point there is the acceleration for that period of structure. So here we're at, let me see. It goes all the way to 5 seconds. So at this point, let's say right here, the first number here is a period, natural period of about 0.5 seconds. And then it's 19, so it's a little more than 0.5 g acceleration at this point. That's the acceleration, absolute acceleration of the structure. Massive acceleration is the force that goes into the column. So it's proportional to that. If I look at a period here of about 0.35 seconds, we're up at above 1 g, 45 point something feet per second squared, so there's amplification. Peak ground acceleration over on the left here is at about 11, so that's about 1/3 g. Okay. If we have a very flexible structure, let's say you have a 3-second period way out here, it's only 1.7 feet per second squared, so it's very, very small. So again, go back to that base isolation idea. Okay, so that's function 2. Now let's go back to our ARS curve, load case, response spectrum, modify, and before we were using function 1, everything else is the same acceleration, U1, function 1. This is a response spectrum analysis, not a time history analysis. We're going to switch it to function 2, but then the scale factor should be what? 1. See, it was 32.2 before because we had it in G. This one's in feet per second squared. So you just say modify, and constant damping ratio of 5%, say okay. So we should be able to save it and then run this analysis, okay? And then we can compare this to the time history analysis for the same earthquake. And you get a sense, do we get back the same results or very different? So let's say analyze, run analysis, and I'm going to say, see the response spectrum, I'm going to say don't run that case. So we're not going to run the time history. It's going to respond. We have to run the modal analysis because the response spectrum is going to use that in the response spectrum. So run that. This will go fast. Okay, it's done. Let's see. Displacements. We don't want the modal. We want the earthquake spectral plot. It's a amplification. So let's scale it. Let's go scale. Scale it back. There you go. actually very stiff, so the displacements would be the same. We can look at that. Let's right click here. So look, 0.41 feet. So we're getting the same displacements that we got from the time history analysis for the same earthquake, because this is linear elastic. The spectral plot is representative of the maximum displacements, right? That's what it's giving you. So it's the same, approximately the same value. If I go over here, and right click, 0.41 round it off. And there's a slight variation because of the axial flexibility of the deck, but relative to the flexibility of the columns and bending, the axial stiffness is much stiffer. So you get, like, I'll right click over here and 0.41. So it's almost the same all the way along the line. Let's look at a moment. We don't have to plot a time history, we just pull off the maximum results, so we can say, show us the moment 3.3, that's it. Zoom in, and look, 20,700, is that similar? From the earthquake time history, the maximum was 20,000 something, right? Over here, we see 12,000. So there's the response spectrum approach, the time history approach. Now when things go nonlinear, you need to go to time history. So let's move on from this and go to, let's unlock it. Now let's go back to a time history analysis using the earthquake motion. Define, load cases. This one, modify. Let's get out of the modal and go to direct integration when we have nonlinear elements. Let's do that. And then click on, don't forget to click on nonlinear, or even if you add nonlinear elements, it won't see them. So just think everything's linear elastic, unless you tell it it's going to be nonlinear. Everything else should be okay. We have to go here and do something. We no longer can say modal damping because it's not using the mode shapes to solve for the damping in the equations of motion. So we're going to, I'm going to click on here, specify damping by period, and it's going to back solve the amount of damping. So you can put in different periods, and it'll actually vary based on the period. And I'm going to say 0. I'm going to give it a little less damping, and I'll explain why in a second. So instead of 5% damping, I'm going to give 2% damping. Okay. And now I'm going to, the reason I gave it less damping is the damping, we gave it 5% when we do a linear elastic analysis, and that's because there's no hysteretic damping. When we do nonlinear analysis, there's hysteretic damping that occurs in the plastic hinges as it cycles around, and that energy is removed from the system. So more realistic damping for the remaining linear elastic parts of the structure is 2%, not 5%. If you do a linear elastic analysis, people use 5% because they're trying to capture the amount of energy that's taken out through the nonlinear behavior. But if you're actually modeling the nonlinear behavior, it's already, and you'll see as it cycles around, each loop, when it's going nonlinear, it's no longer linear elastic, it's no longer a straight line, it's looping. Each loop is energy being removed from the system. It's like equivalent distance management. We need to define a plastic hinge, so let's say define section properties, go down to hinges, and then add a new property. Says concrete. Okay. We don't want, I'm going to call it pH. Plastic hinge 1. Deformation control, I don't want it to be an axial nonlinear behavior, a squishing like this. I want it to be moment rotation. So you click here, you change it. It could be any of these types of nonlinear behaviors, but ours is moment 3 that I'm interested in. So this pops up and it gives you what the moment versus rotation can look like at the plastic hinge. It's rigid, which is correct until the plastic hinge forms, and then it takes on these other values. Click off use yield moment rotation, and we're going to put in our own moment. What do we say it is? 5,000 cubic feet, right? So, and we know it's going to happen because when we ran it, we know we saw 20,000 cubic feet, so it means it's going to have to go past 5,000 on the way to 20-something thousand. So it's nice to run linear elastic first because now we have a sense of what's going to happen. It's going to for sure go 9. Okay, so let's put 5,000. And these other parameters, I'm going to make these a little larger. Let's say it's 0.05. This is the plastic rotation. We can talk later about this. this isn't the cyclic behavior, this is just an envelope for the cyclic behavior. It'll go up until it reaches this point, that's 5, this is the 5,000. And you look at this, it says moment over SF. This is the SF. So at 0, that's that point right there. And then at 1, it's also at 0 rotation. So 1, this is moment over SF. SF is 5,000. So really, this is 5,000. Is what it's saying. It's just so you don't have to type in large numbers here. You can put one number here, and these are just ratios. So and then this is 1.1 or 10% larger. So that's 5,500 kip feet. So it goes up. This on this graph here. This is 5,000 kip feet. If you just push them monotonically, not cyclically. And then if you keep going, this yellow point here is at a plastic rotation of 0.05 radians, and that's at about 5,550, 1.1 times that. That's what this is saying. And then it fails and it drops. But prior to reaching that, in both directions, what happens is linear elastically at first it'll go up and down here, the moment will, without any rotations. See how it's 0? And then if it exceeds this point, the moment gets larger, it suddenly takes off and goes this way. But then when it unloads, it won't come along this curve, it'll cycle. Form a hinge that cycles around. And it's the area under those curves that would take energy out of our system properly. But if it exceeds this point or this point, which I gave it, I said, okay, 0.05 radians. And what that is the ultimate curvature minus the idealized yield curvature of your section. That's ultimate curvature multiplied by a plastic hinge, like the equivalent plastic hinge. Like that gives you a plastic rotation. That plastic rotation, the ultimate curvature is based on the strain capacity of the concrete and compression, and the rebar that's inside the concrete, that strain capacity, whichever one reaches its capacity first. That defines the curvature is the slope of the strain profile across the section. And when it's linear elastic and when it's nonlinear, the strain profile is assumed to be linear across the section. The stresses are nonlinear, but the strain profile will be linear. So we're good, we say okay. Now we want to assign it. So I'm going to throw it in here and here. You don't have to do it to the third concrete that's pinned to the bottom. And we'll say assign, frame section. No, that's not what I wanted to say. Assign, frame hinges down here. And instead of auto, change that to PH1. And relative distance, that's where it is along the member. We're going to say 0 because we know that's at the bottom. It's the beginning of the member. Say okay. Oh, say add. You have to click add or say okay. And there it is. See? Plastic hinge and plastic hinge. Should we do the same at the top? What do you think? Or should we run it and see? Maybe it doesn't need one. Maybe when this forms a hinge, that reduces the amount of moment that's still okay. What do you think? Try it this way and see what it is at the top. And then over there, here, this pin. We shouldn't add too many because, as you'll see, it takes longer to run. And then we'll be standing here twiddling our thumbs. Right? Run analysis. I have to be careful because we said, oh, okay, it's going to run again. I don't need the response spectrum to run. I'll say don't run that one because then we'll accidentally click that. Okay, here we go. So now it's going to run, solve the problem every 0.02 of a second, and if something goes nonlinear, it'll iterate until it balances all the forces, and then keep going. And sum all the incremental results, we get the total results. So it's running. There are 2,000 steps. It's at 190, 200 right now. So it's 1/10 away. It's saying it's converged. It's iterating and continuing. We're at, over here, the total time, earthquake time is 40 seconds. It's 5-point-something seconds into the earthquake. A good rule of thumb is you want to write a computer program that can solve it as fast as the earthquake. So if the earthquake's 60 seconds, you should be less than 60 seconds. But you can see we're falling behind because we've been running longer than 7 seconds. At the top, it tells you we've been running 55 seconds. Those analyses that we're doing on a 30-story building is 1 week of straight running time, and the earthquake's only 60 seconds. So. we're at about 1/4 of the way, 10 seconds out of a 40-second earthquake record. So what happens is, you can see, this is why the industry fights us with, wanting, I'd like to see nonlinear analysis used in everyday design of bridges and building structures. But then when you get more complicated, develop a complicated model, this is just a simple model we have for the bridge, it's not that detailed, right? As you get more detailed, it takes longer to run, and for production purposes, it ends up being a difficult stuff to use nonlinear analysis. Nonlinear analysis is good because it represents the physical behavior of the structure under an earthquake. They're always designed to go nonlinear, but they're not analyzed as nonlinear. Simplifications. Like the divide by 6. So we're almost halfway. We're at 16 seconds right now. While it's running, I think it's fun a couple of things. You'll notice it doesn't continue at the same rate. It slows down when it has to iterate when something's going very well.